Okay, to refresh your memory, the last two topics were about um, the first step into multiple dimensions really is when still have a function, and but this time the either input is two-dimensional or the output is two-dimensional with the other variable that stays the same. Okay, so it total then is a number of dimensions three. So so then when you plot its graph, then you need to plot it in the three-dimensional space right away. Okay, so that already tells you that that's because then we have to fit our graphs on the three-dimensional graphs on a two-dimensional piece of paper. Okay, so that certainly cannot continue on, and then now we're moving yet a little bit beyond that. So once again, parametric curves and functions of two variables, those are the ones. Just to begin with, and now we move one more little bit step beyond, and that is when the dimension of the input is two and dimension of the output is two. Okay, so it is the literally then, as we have discussed, the transformations. We're thinking of functions as transformation as much as we can, and so that was the original one that we started with, and input output is what the reference of the numbers is. And now this is where we are now looking at when both input and output are two-dimensional, which means that the graph lies in the four-dimensional space. So you can twist yourself, and you can there are ways to visualize these, but ultimately it will fail. So we'll stick to this for as long as we can. So we can fix right. So the two-dimensional equation to any higher in the are going to be introduced as much as possible now when we still can see them. Okay, and so then we will be not able to do it anymore. Okay, so that's where we are. So we start very simply. So once again, it is a transformation of the plane, but it comes from a good way to start with it is understanding that we start with dimension one in one, which we know how to transform the axes, one axis at a time, and one y at a time. So let's transform one of the two axes and see what happens to the whole plane. And the answer will be transformation of the plane. Okay, so once again, this is the thing. Up here in a minute. Oh, here it is. So that's, as I said, this is a transformation of the line. So we're still speaking of a very familiar to you functions of one variable, one input, one output, but they're interpreted as transformations rather than, so no graphs, but rather diagram of those arrows. Inputs from input, arrow goes to the output. The three main transformations. This is quite a bit sufficient for linear algebra. The shift, the flip, and the stretch. Naturally, you can shift left, right, you can flip as many times as you like, and you can stretch, and the opposite would be shrink. Okay, so these are the transformations, and here and now we realize we have two inputs, which means that x and y. So these are not, as if you look carefully here at how I use the notation here on the right, it's not y is not the output. Okay, so the now xy is the input. XY is the input, and UV, look at once again on the right, U or V is the output. So you can do it one at a time, and then it will be from X to U, or from Y to V, or from Y to V, that doesn't matter. But the point is that we have to carefully name things so that there would be no confusion here. But the main thing is, once again, XY is the input. So the x and y's, as we saw with functions of two variables, they vary independently. Remember, the domain was an array of numbers, pretty much. Okay, so you can move this way and that way independently, and then the elevation would be the output. So it's almost the same thing, except the output is now also two-dimensional. Okay, so then we can do what we have done before. Shift, flip, and stretch for x, shift, flip, and stretch for y. So altogether we have 3 and 3. So if we start combining them together, we have already a bunch of transformations to worry about. But we do it one at a time, and so one of them then will be a transformation that is horizontal, and the other one will be the vertical, a vertical transformation. Three horizontal, three vertical. Okay, so naturally we're not transforming just the x-axis, but rather also transforming every line parallel to it. Okay, so that the red axis, the red is the x-axis, but we are what we do exactly the same thing to every line parallel to it. So same here. Okay, so the x-axis here somewhere, that doesn't really matter what it is, and then as you can see, every horizontal axis, every horizontal line is shifted. So the end result is you see at the bottom, it is the whole thing shifts. The whole plane is shifted by the same to the right. Horizontal shift by the same amount. The flip now it's more interesting. Then once again, every horizontal line is flipped, which means that the whole plane is fixed. So it's flipped. So like these, they're my axis, and I flip them like this. Okay, and finally, every horizontal line is stretched, and then the whole plane is stretched. It's very easy to imagine, and then, but the point is really not here. The point is really the algebra. Okay, the algebra that we have learned, the algebra right here described here, the one variable transformation of the line, which is like a rubber band. These are the three transformations. The algebra is very simple. And now, if we combine these two together, it turns out it's really not that bad. The algebra is also simple and compact, even though it is twice as much, or four times, right, actually, as much work, because there will be two variables on the right. Okay, so for my formulas. Here. Okay, so once again, three transformations. Look at it. So x. So the left part of the table. The left part of the table is still one-dimensional x-axis. X. Yeah. X forming exactly like x goes to x plus s, while y in green remains intact. Okay. So the end result is x becomes, and then as you can see, every point xy becomes xy. So that's how we did the first row, how we describe a horizontal shift of the plane. Okay, xy goes to x plus sy. As you can see, it's twice as much work, but nonetheless, it's very compact. That represents that transformation. Then the flip x becomes negative x. We do exactly the same thing, but now it's not just the x-axis, it is every x for every location on the plane. X becomes negative x. That's a horizontal flip of the plane in the middle right there. And the third one is multiplication by k. Depending on the k larger than or less than 1, you will get a stretch or a shrink. And once again, y is intact, as you can see. So xy goes to x times k y. Okay, so y is intact. So that's a transformation in one particular direction, in this time being horizontal. Okay, now we do the same thing, the same three transformation, but this time it's vertical. So you can guess that the left part will be the same, but the y's will be changing. X will be stay intact. So once again, the transformations are the same three. We are shifting in the vertical direction. Every line parallel to the y-axis is shifted, and then or every line parallel to the y-axis is flipped. Every line is stretched. Okay, so if you imagine that probably is something to look at. The first two are your plane is intact. You just shift it or flip, but it is the same. Nothing happens to it. And the other is stretched. So you can think of this as rubber bands. Okay, so each of these is rubber bands, and then they glue together. Okay, so then together they have a rubber sheet. So that's how we understand now the XY plane, rubber sheet, and then we can stretch it if we want. We can flip surely, but we can also stretch it. Okay, in any direction that we want. So this is the algebra. Okay, once again, the three transformations. Once again, look at x. The red axis remains intact, so because we concentrate entirely on the vertical transformation, and then y. The formulas are the same. The algebra is the same. Y becomes y plus s, or becomes y, or multiplied by k. These are the three transformations. Okay. So that gives me 6, and then just the rest you can see if is it obviously not. Okay, so we have even if we just even if we just take the same transformation, but apply that, we can apply the three transformations for any direction. So we can shift in any direction, we can flip in any about any x, and also in so it's there. Then we can still combine them together. That's especially easy to see if you go to this Microsoft Paint. Okay, so a vertical shift, executed literally. You just grab that window and move it apart, move it to the side. And they all these transformations actually have special buttons there. Okay, so vertical flip, literally, what's the language that they use? Flip vertical, right? Flip vertical. That's the drop down menu. Flip vertical, horizontal, rotation 180 degrees, which is surely is to be worried about. Vertical. This is vertical vertical stretch. So as you can see, it is. I believe it's 200. The left picture on the left. It's unselected maintain aspect ratio at the bottom left. You see it there. Okay, so which means that the 100 on the horizontal remains the same. Nothing, no change in the horizontal direction. The vertical direction there is a stretch by 200, and that's that arrow a star on the left because that becomes that stretched arrow on the right. Okay, and then the same thing happens on the right. The only thing that we have not covered here is rotation 180 degrees. Okay, so and we didn't do rotation. Definitely, it is another transformation. But so you can think about so how do we can we execute 180 degrees rotation in the manner that we have discussed? Vertical flip, but that's not it. And horizontal, right? So yeah, two transformations combined together, horizontal flip, vertical flip together, then they will all together it will be executed as a rotation 180 degrees. Okay. So so once again, let's quickly look at what it looks like. All of these transformations. So the shift piece of paper shifted. So you have two, one for reference underneath that pink grid for reference, and then the sheet of paper with the grid on it is shifted. Okay, you see where the point goes, and then that point is transferred onto the grid that underneath, and that counts as the transformation. Once again, the algebra. now look at it. The carefully look over here. It is we now think of what we do as a function. Okay, so the function is it has a formula on the right, but it also has input xy and output ub. Okay, so two-dimensional input, two-dimensional output, and that's literally the domain is the plane, and the different plane is the codomain. Okay, so this is my shift or translation. Okay, this is the flip. So we still doing everything horizontal. This one is, hold on a second, why is it? This is a horizontal shift, and this is for some reason vertical flip. Okay, well, whatever. A vertical flip. So once again, a piece of paper flips on its other side, and then you can see where that violet point where it went. Okay, so once again, the formula, as you can see, just this literally, this is the function. So if you have seen before, if we have x equal to say negative x, so that's the way you've been writing it for a while, dealing with functions of one variable. That's how we're going to be doing functions of two variables, two inputs, two outputs. So there are two outputs to worry about, and each of which is a function of the variables. Okay, so we are looking at the simplest one. That's why x appears here and y appears here, but they do not cross. But that's not gonna be forever. So like I said, there will be always there will be x could be on the left and on the right, and so does y. Okay, so we'll see that in a minute. This is a horizontal flip. Okay, so once again, a piece of paper flipped. This is the algebra. We already saw it. This is the vertical stretch. As you can see, this time it's a rubber sheet and with a grid, and you can see what has happened to the grid. Those squares have become rectangles, and then we transfer the points one at a time on the underlining underlining domain. So the codomain, the pink, sorry, the blue grid has been stretched, and then all the points on it are then placed on the codomain, which is on the right. Okay, so once again, this is the domain, the blue one, and this is the codomain. And this is the function. So once again, a function is not anymore just numbers, but in this case too. Okay, so this is the algebra, the stretch. Think about the stretch is very easy to misunderstand, but it is a stretch away from the x-axis, or in this case, from the x-axis. So imagine that x-axis is actually nailed to the underlying table, say, and the rest of it is rubber band, and you start stretching away from it. That's what the stretch is. So as you can see here, the location changes too. So every square doubles in size that the stretch is. But the second question, where is it? And that you can see where it is. It actually moves to, because the holes, you're not stretching anything on the plotted on the graph, on the XY plane, but rather you're stretching, it is drawn on the graph, and then it's drawn on the that rubber sheet, and then as you stretch rubber sheet, it is stretched to whatever is written drawn on it. Okay, so the collapse, remember that's the one that we also worried about, the collapse, the special operation, and it still works, and the operation is kind of interesting. So you look now carefully at what's happening here. On the left, once again, every axis is every vertical line is transformed the same way. The whole line is collapsed to a point. So but different point, a point on it. So the purple line goes to the purple point, the blue one goes to the blue point. Okay, so and the yellow to yellow, green to green, and altogether, then what we produce is called the projection. Okay, so the whole plane. This is the plane, and what the image is. I'm not speaking of the codomain, but the image. What's the image? The image, the range. What is it? So domain is the plane. Codomain is also the plane. What's the image? Remember what the image is? What is the image of a function? The image. Okay, so if you go back to pre-calculus, the term that was used was the range. Okay, so what's the range? What is the range? What's the definition of the range?
Values.
All actual y values, right? So if you skip from y, x and y's, let's speak the language of what we have here. It is the outputs. Okay, so because now y's are just part of the input. So the range is all actual, not potential outputs. So a codomain is all potential possible outputs. Okay, and this is the actual outputs. So as you can see, in green, these are potential outputs. The actual output are colored. Okay, so because every axis is not just shrunk, it is collapsed to a point. So altogether, the range, the image is it is entirely the x-axis and nothing else. So that is very similar in a way to to the collapse. A one-dimensional thing becomes zero-dimensional, so the whole line becomes a point. And in this case, once again, an extreme singular, the word that we're going to be using, singular transformation. That is the plane becomes which is two-dimensional, becomes one-dimensional. So two-dimensional plane becomes one-dimensional line. This one-dimensional. This one is two-dimensional. Okay, So once again, look at the algebra. It's very simple, and you can see the second coordinate is always 0. That's what the x-axis is. And x stays, okay, so it stays intact, and then in the meantime y becomes 0. So that's literally what a constant function is. So all y's go to the same value. Y goes to u equals if equals 0, and that's the collapse in the vertical direction produces what we call a projection. You can see why it's called a projection. Does the word kind of ring a bell? Why would that word be appropriate here? I'm not sure if you project, you know what a projector is. You've seen projectors? Okay, so you see how it might work. Yeah, so it's literally think about it. Projector cast an image on the screen. Well, in fact, so this is that example, but next door we have an actual projector instead of TV set. So there's a camera, not the camera, but rather the projector hanging there, and it casts an image onto the plane. So something that is hypothetically is three-dimensional, it will cast the image on the two-dimensional screen. And if you don't see how it is originally three-dimensional, think about shadow. So that's another way to see it is a three-dimensional object will have a cast shadow on the plane. Okay, so that's projector is kind of an appropriate word, even though some of the connections may have been lost. Okay, so once horizontal stretch, same story. This is the algebra. This is the horizontal collapse. As you can see, the end result is the image is the y-axis this time. Okay. And once again, the formula. These are our 6 basic transformations, the basic transformation to begin with. Okay, so the original picture is on the left, and then I have going straight horizontal shift, horizontal flip, a horizontal stretch. Okay, actually, it happens to be a shrink. Okay, so that this is the shrink, so it's like shrunk like this. Okay, and then I go with vertical shift, vertical flip in the second row, and then a vertical. This one appears to be a stretch actually. So this is shrink. This is stretch, if I'm not mistaken. So no, hold on a second. It is shrink. It is shrink. Just like this. I was looking in the wrong place. So this is still a shrink. You see, this is a shrink. So it's that original picture on the left. It became kind of a narrower. That's the shrink. Okay. So once again, a transformation of the plane. Input R is R2. The domain is R2. Output is the codomain is R2. Nothing but a formula. So what unspecified, we can study any one that we want. Okay, so input and output. So U depends on X, Y, V depends on X, Y. If it's not, so U, yeah, depends on X, Y separately or together. That doesn't matter, generally speaking. We just like to collect them together so that we could produce points and vectors on the plane. Okay, so in order to visualize it, so rather than the way I described there on the right is one number depends on two numbers. Another number also depends on two numbers. So that might not be very revealing about what's going on, but if you start thinking about X, Y as a point, well, then you can think about transformation. Then you combine U and V also into a point. Okay, so all of these, this is a point and that's a point. In which case you can start, visualizing, have something more tangible in your mind about what is that little formula does. And so what it does, it transforms the plane. Okay, so once again, these are the formula, whether you have the name for the function or not, these are the formulas. Once again, if it's entirely vertical, then the second coordinate is changed and the first coordinate X is unchanged. Here is if it's horizontal, then you have the opposite. X's are changing, Y are not. Y's are not. Okay, so these are our 6 basic transformations. And then you can combine them consecutively, look at it. So anytime you want, naturally the word is composition. So stretch vertically by K and then flip horizontally. So two, you can, when you have two, you can have as many as you like. And then you can retranslate that to the first row is a verbal description of what's supposed to happen. And then you describe it algebraically in the second row. So if you want to stretch by vertically by K, that's what's supposed to happen, right? Y become K. And if you want to flip horizontally, then negative X is X becomes negative X. That's the flip. Okay. So any questions so far? Okay, so once again, this is one thing, and you can have any transformation that you want. On the left is a kx, ky is what? Can you be more specific?
Plane horizontal.
And horizontal, and with the same coefficient, which means that it is the right described as a rescaling. So it's the same. The shape doesn't change. Just the size changes. Okay, so once again, if you go to Microsoft Paint, you just mark the aspect ratio. Yeah, aspect ratio. Not a mathematical term. So when you stretch one but not the other, then you're not maintaining the aspect ratio. So and then I have here shift in the middle. I have shift and horizontal and flip vertically, and then the end I have horizontal horizontal stretch, and then I have a vertical stretch and shift. So as you can see, the variety, even from those 6 operations, you can produce such a variety of transformation very effectively. So once again, there's scaling here. This is the aspect ratio, whether it's marked or not. This is a star has the same exact shape. And over here we have a 180-degree rotation, one operation if you don't split it into. Okay, so there's some exercise here. So let's look at something familiar, even functions. Remember even functions look like this. We understand them now. We're using this new language. We understand them as they are being subjected to transformation. And in this case, it is a horizontal flip, and the graph lands on itself. That's what an even function is. Remember an even function, you write it f of negative x is equal to f of x. Okay, so if you ever wondered about it, now we have a different look at it. It is, once again, it's a curve, it's graph, which is on the right, when that it is drawn on the xy plane, and then we transform the xy plane by flipping it horizontally, and what happens to the graph? The answer is nothing. Okay, so it's called a symmetry. Generally, so specifically it's called the mirror symmetry, but with all these transformations at hand, we can try to understand what symmetry is. And the symmetry is, or any symmetry is, something, not the definition really, that is preserved under transformation. So then the issue of symmetry becomes, what is that transformation we're looking at? So also as far as the flip, so that's a horizontal flip. So what is preserved on the horizontal flip in addition to even function? That's fine. That's just to make a link to pre-calculus. But really, what it preserves is a mirror. What is it preserves is a mirror symmetric objects. Okay, so mirror symmetric, which is you see everywhere, mirror symmetric. I don't know, the Parthenon or something like that. Okay, so mirror symmetric objects are everywhere. So here we go, and then we understand it now differently. We once again, it's a two-dimensional picture. We flip it, and then it lands exactly on itself. So the facade, typically in whatever temple or whatever, is symmetric. Mirror symmetric. Okay, so another way to see it is you fold it on itself. That's just a second odd functions. It is once again it has symmetry, and it is preserved on 180-degree rotation. Okay, so a graph on the left and top left, and we start rotating it gradually, and then at the end it lands on itself. Okay, so and then it make a full trip, and then it's exactly the same thing. So that's the symmetry. So the transformation is the rotation, and then whatever is preserved under that rotation is called central symmetry. So central symmetry as opposed to mirror symmetry. And then it's not as typical, but nonetheless, this is central symmetry. Describe one point at a time. Through the origin, you find the corresponding point on the other side. Unlike in the mirror, you look for the corresponding point on the other side of the mirror. That's what you when you do with the mirror symmetry. Central symmetry, you look for the counterpart on the other end of that line that passes through the origin. Okay, so that's what you see in this picture. Okay, so and once again, now we're not looking at it anymore separately, just something special, but rather just another transformation. Every transformation will have its symmetry. So we have two. We have a flip, and that mirror symmetry in the horizontal direction. You can have the other one too. That's no problem. Vertical too, even though you don't see temples with that with the kind of with that symmetry. And then we have looking at a different transformation. It has its own symmetry. So every transformation will have a symmetry. The formula is very simple. When 180 degrees, either you think of two flips executed consecutively, you just multiply both negative x, negative y, x by negative 1, and that's the transformation that you can see here. So, oops. And so then the just in case you don't remember the formula, that's f of negative x is equal to negative f of x. So if we were to see the symmetry of that function, such as x cubed, it is odd in that sense, and so that's the odd because the power is odd. But otherwise, it's a symmetry preserved under rotation 180 degrees. Okay, so here's the third transformation that you saw in calculus, pre-calculus. That's how we produce inverse functions. Okay, so you literally take the graph of the original function and flip it about the diagonal. So flip about the diagonal. So just like itself, one point at a time, shown in the first picture. In the second picture, you can see, imagine that it is drawn on a transparent piece of plastic, and then you flip that piece of plastic, x becomes y becomes x, and that's what finding the inverse of a function is. Okay, so and the transformation, look at it, the transformation is still very simple but new. So we up until now, every example we had was look at it. The x is here and y is there. So y goes to somewhere, and then x's are still in the same, remain in the same place because we were only thinking about horizontal transformations separately from vertical transformations. In that case, you have even executed consecutively, x's go to x's and y's go to y's, but you can intermix them easily. Okay, so that's the intermix. X becomes y and y becomes x, and that's literally what we want from the inverse function is whatever was used to be input becomes output. Okay, so and that's once again very simple formula giving you this this idea. So and then once we take that route of intermixing x and y, then we realize that that is not an exception. It's a rule. So most of the transformation like that, rotation. Think about the rotation. This is a very simple rotation, and then you can see once again how x's become y and y becomes x's sort of. So and then you ask yourself, what's the formula? Can you think of the formula? A rotation 90 degrees. Well, ask yourself, where does x go? What happens to x and what happens to y? Do you see the intermixing here? The flat part of the triangle used to be on the y-axis, now it's on the x-axis. Okay. Okay, so what does it tell you? So if I once again. The what who becomes negative? Oh, hold on. yeah, they are intermixed. Okay, so let me write it here, x and y, and then the issue is indeed the sign. We just need to determine which sign, right? So this I'm sorry, yeah, we intermix them, right? Y and x. Okay, the question becomes the sign. Okay, so it's not the same as this, right? So when there is no sign, we have a flip about the diagonal y equal x, the diagonal. So that's not it. So then, but the intermixing is there. We just need to determine which sign it is. It appears that what happened to y, y becomes x, right? And look at the red, or what I marked in red. That's the y, and it becomes x. So y becomes x, which means that we have a plus sign here, right? And then we'll probably have a minus sign here. So x, I'm sorry, y, unless I'm mistaken, y goes, I'm sorry, x goes to -1. Or rather y, this is u, well, let's be clear, u and v. If you were to discover this in a kind of a consistent way, then these are, let's be clear, let's name things properly, u and v. Okay, so x and y, and then it's not that y becomes y is matches u, right? Y, whatever was y, hold on, so am I right here? Let's once again. Okay, so y, let's look at x. So x, whatever that value of x was here, it has become, it dropped down. But that's the variable of u. So if I take 1, 1, it becomes 1, -1. So the second variable is nope. The second variable is negative. Yeah, I think I'm right now, and not what's written there. So the second coordinate is negative. Okay, so okay, let's check. Am I right here? Y negative x is the formula. Right here. So that point over here that used to be 2, 4 has become, what has it become? 4, -2. Okay. So the second coordinate is flipped. If I flip, what do you think is this? What transformation is this? Well, we tested this, and now this question is that. Right, 270. I would rather say 90 degrees in the opposite direction, but yeah. Okay, stretches, all 6 together. Rotation is still to be every angle, by the way, is available. So we'll have to have a formula, which will be more complicated than that. So when you have only 90 degrees, one particular very special rotation, then you don't need to do anything complicated. Formulas very simple. But if you need to rotate 15 degrees, for example, there will be x's and y's present on both left in both of these coordinates, so they will be somewhat complicated. We'll get to that. Okay. So let's more linear transformations, and we have had some linear transformations, and then we're gonna concentrate on specifically on linear transformations. And one of the somewhat dramatic things that we're gonna do, we drop the shift. The consideration there just too simple. Okay, but let's now think about transformation of the plane to the plane once again. So let's be clear, we're sticking to that. But to understand how they emerge, let's find them in the problem that we have already done, the problem of mixtures. And so, but let's do it first for dimension 1. Okay, so problem of mixtures when you have, remember, 2 types of coffee. But let's see the functions first. In the one-dimensional case. So we have a type of coffee for $3 per pound, and how much do we get for $60? And that actually we can just go straight to, as we did before, we introduce variable, x is the weight of the coffee, and then the equation that we have produces 3x is equal to 60, and then we divide by, x is equal to 60 divided by 3, we're done. But really, let's imagine that we don't want to solve it, okay, which sounds strange, but it is. The idea here is to set up the problem in such a way that we can use that understanding in higher dimensions. Okay, so then what this is not an equation to be solved, but rather it is an equation. Okay, so not even an equation, it's a function with a known output. Okay, so 3 input is equal to 60. That's the way we want to see it. Because solution involves division. If we just divide 60 by 3, that's surely easy, but in high dimension there will be no division, unfortunately. We know that already. Okay, so then this is how we want to think about it, is once again the function that happens to be so simple, but that's not relevant, but rather it is so the function with input produces the output of happens to be 60, and we know, and then we need to find the input. So as you can see, it is an equation, and it is, we're working backwards from the input, from the output to be known, okay, to find the input that is unknown. Okay, so that's the general outlook that we now want to see. That once again, so let's take this in front of us. It's right in front of us, and it is a linear equation. It's just to make life easier, but otherwise, it's a function with unknown input that produces unknown output. So that's what we want to see, and we want to take this understanding and bring it to high dimension. High dimension is once again the problem of the mixture. So, but before we do it, this is once again why do we necessarily solve the problem by division? We can just match the values. So the values are x's are 0, 1, 2, 3. The total cost multiplied by 3. So we pre-compute our function as a table, and so we have a bunch of x's and a bunch of y's paired up. And so if you need to find the output of being 60, you just find it in the yeah, so and then yeah, so and then you without having to do any computations, you can just go on, and you have whenever you have 20, right, and 60, and so hypothetically you can solve the problem without actually doing any division, just examining the values. Okay, so total weight, total this is the data. In fact, you could that's the reference, and well, actually, the advantage here is what's worthwhile in this setup is like what if varies. Okay, so maybe tomorrow we need 55. The total cost of the mixture to be $55. Is there a way to solve this problem with once and for all? And the answer is, once again, if you have the table of pre-computed values of your function, then you can just either examine it with your finger, or if you can do this, which is this is a spreadsheet, and once again there's a lookup feature in the spreadsheet that will find you looking. So it will go through the right column. Okay, so it goes through the right column and then gives you as the output the corresponding value in the input column. Okay, so it literally will go on. There is no name here, but it is lookup function of itself. And once again, if you are, for example, interested in the total price of 13.5, it will give you the output that you need 4.5 pounds of this coffee. Okay, so it's a very simple situation, and that's why it looks so simple. And instead of dividing by 20, we're doing this weird stuff, but it will pay off once we go to higher dimensions, because there's no division in higher dimensions. Okay, so what we want to understand here is right here. It is a function, and then with the known output, and then we find the input by taking the inverse. Okay, so that's what it is. So that's an equation to be solved. This is how we can at least attempt to solve this problem. So x, the input that we're looking for, is simply the inverse of f of that function, and then look at it. If you find f inverse, then works. The method works for every u. Okay, so that's the good news. The bad news is finding the inverse might be challenging, and might not even exist. So that's a possibility for us to worry about. But at least this is a plausible, feasible approach. Okay, so all right, so let's go to two dimensions, and so two unknowns. Once again, the problem is familiar. Exactly the first day of classes. That's the same exact problem. So we have Kenyan coffee, $2 per pound, and Colombian $3 per pound. We supposed to have 6 pounds. X plus y is equal to 6. The total cost should be $14. So it's 2x plus 3y and equal to 14. These are the two equations. And then, well, we were not seeing this here because there are two variables here and two variables x and y. But now we already know what we are empowered with our transformations. X and y are the inputs. Okay, that's the way to think about what the whole discussion has been about. Is X and Y are the inputs. What are the outputs? So if we were to recognize a transformation from R2 to R2, what are the outputs? So if X and Y were known, then we can just plug them in and find these. The total weight and the total cost. Okay. So then this is the function becomes with two inputs, two outputs, or two point and a point. So the inputs are the weights, okay, and the outputs is the total weight and the total cost. Okay, so that is the function that we are now prepared to deal with. Okay, so remember we solved this problem with we had the geometric representation, all of that business, but now we have a different point of view. We want to say a function and then set up a function with inputs and outputs, and that's what they are. X and y are the inputs, and 6 and 14 are the outputs. And so once again, the outputs, just like in this problem, the outputs are known and the input is to be found. And so the input is 2 points now. So we are resetting the problem in this new environment with a new point of view. Okay, so the total weight, once again, you have, let's combine them together. So total weight is x plus y is equal to u. So that's one how to do slowly. You just say, let's suppose the total weight will be the new variable or the output of our formula. So we're not trying to solve the problem, but rather just trying to set it up. And we can sometimes you can imagine that you can go from input to output. So if you do know the how much of each of the types of coffee you've got, then you will know its total weight as well as total price of the blend. Okay, so these are the two variables. If x and y vary, okay, so if you imagine x and y vary, then what else varies in this situation? The answer is u and v vary too. Okay, so the total weight and total cost, and that certainly sets up either two functions of two variables. Okay, so that's familiar right now. This is more familiar than something else that what we're coming up. So it is familiar. Two functions of two variables, right? So xy produces u, and xy produces v. Two functions of two variables, which we know how to handle. Then think about it. By the way, so what's the remember what the graph is of a function of two variables? The graph of a function of two variables. How do we visualize a function of two variables? So two numbers input and output is a number. So we have two of them, but each of them can be visualized how? Yeah, coordinates, and so x and y on the plane and u is vertical. So together, what do we get? We get a surface. the graph will function to variables to the surface. Okay, so once again, these are the two functions. Xy goes to u and xy goes to v. Okay, each of which will be because everything is linear. One with visualization of the each of these will be a surface. That surface will be a plane. And so you can see the complexity that we're facing. We have two functions, each of which is the surface, and how do you combine them? And they're apart from each other. Okay, so that's why we don't stop here and just try to deal with them separately. We cannot deal with them separately, and the visualization itself is not very productive. So we have two surfaces. What do they have to do with each other? The answer is nothing, because u and v are living in separate places. So even though the xy plane in either case is xy plane, the third dimension is different, right? So if we were to visualize this xy, and the third dimension is v, so it's a different one, and they even have different units. So visualizing, we're dealing with these two functions separately will hold us back. So instead, we're looking at it this way. So x and y together produce u and v. Okay, so either you think of two numbers producing two more numbers, or more likely, we produce a point and a point. Yes.
I'm sorry, this thought just came up. If we're doing the test Thursday on
Yeah.
that online work, does that mean like for Thursday, like everyone has to bring like a laptop of some sort?
No, you do it. First of all, let me, before I forget. So the cutoff point is here, right here. Okay. So so you do it wherever you want, and you don't have to show up here. It's just any computer would do.
Oh, so we don't have to like do it in class?
No.
Okay, I see that.
Just keep in mind it is 50 minutes. So it's not the full length.
Was that 50 minutes from when we start or
Yeah.
from a class?
So it starts at 11. So from 11 to 11:50, and then the answer will be known within an hour after it's over. So once again, cutoff point. So everything up to this point will be on the test, and what we're doing right now will not. Okay, so I'll whatever, if anything comes up, just let me know, and if I think of something, I'll put it an announcement online. Okay, so all right. So once again, two functions visualized by surfaces can be represented as a data for every pair xy. You compute a number that is the cost. Okay, I'm sorry, the weight on the left, cost on the right. So once again, not keeping them apart, we know that there's a better way to do it, and you just start combining them together into one. But before, let's take another look. If we were to solve our problem with the data that we have, okay. So to find the weight that produce to find the weights that produce a total weight of 3 pounds, what do? We find 3 pounds on the table right here. Okay, so this is the weight on the left. So each 3 is found in the table, and then each point will have a combination of weights: 2, 1, 3, 0, 2, 2. I'm sorry, 1, 2, and so on. Each of them can be found by lookup procedure. Okay, so then if you want to also the weights x and y that produce the cost of $7, you'll find that $7 over here. Okay, so and just don't assume that there's only one. And because the data is incomplete, the fractional values are skipped here, so there will be more here values if you were to find them. And then and if you want both 3 and 7, then what you have to understand that it's simultaneously your x and y have to simultaneously satisfy what's on the left and what's on the right, and you remember what it means. It's just two straight lines intersect. Just to refresh your memory. Okay, so it's not very effective way. And so, then if we were to go backwards, that's once again lookup procedure for the two tables using this filled in with those two formulas as we have produce them, and then you can go backwards. Once again, the yellow one is what we want, and then the lookup procedure will give you x and y. It does it twice, and so you have to match up that somehow later on. Okay, so it's certainly possible. These are the markings. They are skipping each other. Therefore, when you look for intersections, you know that they're supposed to intersect because these are not they're not there are no gaps, and so there is an intersection always, and so you can find it eventually. But that's not what we're after. So having two functions of two variables, which is what we kind of upgraded our initial approach. Having two functions of two variables, the data is here. Lookup procedure simplifies things without solving the problem, without actually doing any algebra. And then but we are going through this into to the next level. Pairs. Okay, so not just x and y, two numbers producing a unity, two numbers, but rather x, y right here. X, y is the input, a point, a pair of numbers, and uv is the output, a point. That combination of the weights of two types of coffee on the left, and that's xy, and uv are actually do not match in any way. The first one is the weight, but the second one is actually the cost. So everything is measured in pounds, xy and u, but v is measured in dollars. Okay, so all right, so then this is the function. Now, if you were to combine, look at them. So xy, so in each x is a row, y is a column, but then if you look at the pairs are right here. That's my input. 719 is my input. Okay, and then I carry out the computation with those two formulas and I end up with data. These are the outputs. So once again, 4 and 2 produce 16, 14 is the output combination of two numbers. The two outputs that actually now look one point. So it's literally the inputs on the left produce the corresponding outputs on the right, and really what we only need is what's on the right because all x's are already there, and then the body of the array is filled with the outputs. Okay, but the outputs are not numbers anymore. As you can see here, it's hard to implement. I think with the, as you can see, that's how you implement the table on the right with Excel, and that looks kind of awkward. But you know, if you want to write code, that's very easy to actually do. So input to numbers, output is a pair of numbers. Okay, so pair of numbers, and that's, we know what it means once you see it. It looks complicated, but it's not unfamiliar. It is a transformation that we have seen, and not one that we have seen, but surely we can classify it as, if not one from a simple list, as a combination of those. Okay, so we have the way x and y are, where's my formula of x and y? So x plus y, so once again, let me write it, u is equal to x plus y, and v is equal to whatever 2x plus 3y. So once again, these are the inputs, x and y are inputs, and uv outputs. So the formulas are very simple, and that's why it falls into the algebra entirely. So there are no complicated functions. So once again, these are the functions. This is the step that is important, and the big one for linear algebra is to understand that yes, everything, if you have x, y, you combine them into x, y point, and if you have uv, combine them into uv a point. And that's the algebra that's written at the bottom here is the way we're going to treat it from now on. Okay, so we are pretty much we cannot possibly leave it behind, but this is becomes outdated. Okay, outdated. Just dealing with numbers, we're dealing with now with points. So it's a linear operator. It doesn't look the same as we have seen. Just to refresh your memory, that we had x minus y, we have yx, we have 2x, 3y, like that. These are the transformations we have seen, and this is the same story, only slightly more complicated. And in fact, the algebra that we're looking at is not. So it's still, look at it. What happens to x and y? Multiplication, which indicates what? It indicates subtract, right? And then addition indicates, well, not clear what adding x and y, what it does to the graph, but rest assured, we'll see how to see simple transformations inside of this. So how to decompose this more complex transformation into simple ones. So we'll do that later, but nonetheless, so that's what I just said. Once again, is the problem now, the set of our problem is here. So once f is defined by this formula. This is my problem is now looks like this. For f of 4, 2, well, it's the answer, but the question was f of xy is equal to 614. So that's the problem. And then somehow we still don't know how exactly that's the solution. So 4, 2 is the solution, and indeed, when we plug it into my function f, we have it with 614. So to visualize, if we have a plane, xy plane, it's transformed into the UV plane. With 4, 2 going to 614 happens to be what we want, but maybe tomorrow we need a different blend, so we're not going to stuck with 614 here. So then the reality of how it happens, if we were the inverse of our function f was available, then it doesn't matter what tomorrow the blend that we want to construct, we will be able to find the appropriate x and y on the left axis if we had just had f inverse. Lookup works if you have data, but as you can see, the data is always incomplete because of the gaps in that table. So we'll be thinking in general as a transformation of the plane, and then the inverse transformation of the plane is for us to worry about. Then some of the things we have seen, right? If we stretch horizontally, then what's the inverse? Shrink horizontally. Okay, flip. What's the inverse of the flip? Another flip, right? So we can do some of that. So it's certainly is a good plan. And that's now this is the view on our mixture problem. Is once again the function is given from the problem, and we just whenever the output is given on the right, we need to find in the opposite going backwards to find where it came from. Okay, so that's how we solve these problems. It matches, remember that's dimension, we have x to use a f, and we had a very similar situation with a one-dimensional case. And now we have switched to two-dimensional case, but the same idea goes to u, but in specificity, say 60, and then you have to go find x using what? Using the inverse of f. So then remember it was multiplication by 3, right? Well, that's my f, and then f inverse is division by 3. So we can still interpret what happened in that elementary one-dimensional case in that language. So there's a transformation of the line to line. What was the transformation? A multiplication by 3. What's the inverse of multiplication by 3? It is division by 3. So that's such a kind of more advanced point of view on a problem that really is elementary, does not require any of that, but it's good to know that the new approach that we have will be applicable to all dimensions and beyond dimension 2. So once again, just for a moment, so if this is dimension 2, dimension 3, so 3 ingredients, okay, 3 ingredients, and then separately, dimension 3, there is no such thing as dimension 3. It is more like a let's write it. This is 1 plus 1. This is 2 plus 2. And here we could have 3 plus 3 if you have not only have 3 ingredients, but also you have 3 requirements. Okay, so but let's say that's the case. 3 ingredients and 3 requirements, and then the visualization will be the same, but this time it will be 3-dimensional space transformed to another 3-dimensional space. And once again, a particular combination of those outputs that is given, we're supposed to move backwards and find the input that would assure that the condition is satisfied. So naturally, visualization becomes less and less obvious and less useful. And then dimension beyond 3, it cannot be able to visualize it. Then you have to learn how to visualize going through these dimensions higher and higher. So the multidimensional space, you should be able to also to visualize, if not on a piece of paper, at least in your head. Okay, so the cases of when, remember what we discussed this a little bit. So when the function is modified slightly, there is no inverse. Okay, sometimes. So because the issues, as you remember, of the existence of inverse, the function has to be one-to-one and onto. So the inverse is a requirement for this problem to be solved in this fashion. And so the question becomes: is f one-to-one and onto? It appears that it is, but they're easy to modify where it's not the case. This one is not onto. It is actually a projection. Okay, this one is a projection. The whole outputs are actually a straight line. Okay, so another possibility is this, when there are, once again, this one is not one-to-one, and therefore there are infinitely many answers, which is, you know, what do you do about it? Nothing you can do about it. Okay, so once again, we're looking for the inverse. These are the lines. The inverse of so is it one-to-one? And so it appears that how do we know that it's not one-to-one? Because there are output, the same output is repeated 612, 612 is repeated infinitely many times. We will for sure know that's not one-to-one. We can discover it algebraically if we realize that what is it? That there is a relation between the two, as you see over here. So if this is my function, I remember that we have 2x plus 3y, and if I were there, that's the original, I replace it with 2x plus 2y, and that ruins everything, because now there is a relation between u and v. We're looking at the image. We're looking at the image of my function. This is my new function. This is the old function. This one is new. Okay, and then I'm looking at the image of f, and then I realize that with this formula, it will not cover the whole plane. Okay, why so? Because no matter what x and y you plug in, u and v, the outputs will be related to each other by this formula. You see that what happened here? Right? You see? So x plus y multiplied by 2, you have 2x plus 2y. So that's establishing a relation between u and v, which means that you cannot step outside. This is all unavailable. Okay, it will be only one straight line where you're gonna be hitting. Okay, I'll stop here, and so next time I'll see you will be